Okay, subtopic 10.4, which is on application of standing waves. So in this subtopic, you should be able to solve problems related to the fundamental and overtone frequencies for stretch string, air columns both open and closed end, and lastly use the wave speed in a stretch string. Okay, so this progressive transverse wave is produced when this string is plucked. Okay, so when this string is plucked, the wave will then be traveling to both of these fixed ends here, causing it then to be reflected back lah. Okay, so it will be reflected back. So when it is reflected back and then meet up at a point, there will be a superposition of these waves. Okay, so this superposition of waves, for example, when it occurs here, it will cause the formation of stationary waves. Okay, as can be seen here lah. Okay, so the string will then form one segment, which is a loop, and then this pattern of this vibration can be known as fundamental mode. Okay, which is at the first harmonic mode. Okay, so this fundamental mode is also known as fundamental frequency, which is F note. Okay, so the stationary wave forced on the string causes the air to vibrate. The stationary force the air to vibrate and produces a sound wave. Okay, so if the string is vibrating in the fundamental mode, the sound wave will produce a fundamental tone. Okay, if it occurs when the sound wave, frequency of the sound wave is equal to the frequency of the string vibration, it is known as resonance. Okay, it is known as resonance. Okay, so this table is very important. This is where you will be asked lots of questions, and you have to be able to know which at the first harmonic, lambda dia equal to berapa, second harmonic, and then all this lah. Okay, so for the fundamental, which is at the first harmonic, the wavelength is equal to 2 times L. Okay, so this is half lambda. Okay, half lambda. So if we rearrange this, lambda is equal to 2 times dengan L, the length of the string. Okay, so untuk first harmonic, the frequency can be calculated using this equation here. Okay, and then untuk dia cakap di sini untuk wave speed tu kan, wave speed in a stretch string, you can use this equation here. Tapi untuk first harmonic, you can also use this equation in order for you to find the wave speed. Untuk stretch string saja, dia guna yang ini. Okay, lepas tu untuk first overtone, which is the second harmonic. First overtone, second harmonica. Jangan kamu cakap first overtone is first harmonic. No, first overtone is the second harmonic. Okay, untuk second harmonic, the lambda is equal to the length of the string. Okay, meaning that the frequency at the first overtone is equal to this equation here ataupun this one. Okay, and then for the second overtone, which is the third harmonic, the lambda is equal to 2/3 of the length of the string. Okay, so the frequency at the third harmonic, we can use this equation here. Okay, so if you see here, you can actually kind of see a pattern where the frequency untuk the first harmonic, kita akan dapat 1/2L. Okay, 1/2L. Lepas tu untuk the second harmonic, we will get 1/L sahaja. And then untuk the third harmonic ataupun the second overtone, it is 3/2L. Okay, so dari situ kita boleh dapat, meaning that in general, the only number that is changing is the value of n. Okay, so the value of n is the one that it's keep on changing. So the n is referring to a number of segment ataupun harmonic. Okay, it is referring to the number of harmonic. So this is third harmonic. We can see yang di sini tu 3. And then if second harmonic, di sini sepatutnya 2. Tapi dia sudah cancel dengan yang half tadi, over 2L kan. And then yang first harmonic is this one here. Okay, so you can actually already see a pattern. So we can directly use this equation untuk stretch string. Okay, tapi the only trick here is you have to know dia which harmonic. Okay, which harmonic. And ni it tells us about the harmonic. Okay, bukan overtone. Harmonic. Okay, itu yang kamu perlu remember. So basically, it is only valid if the length of string is constant. For example, piano, violin, and guitar. Okay, so that is on stretch string. And then let's look at for wave in an air column for closed pipe dulu. Okay, untuk closed pipe, one end of the pipe is closed lah. So this we will be using a tuning fork to disturb the source of sound. Okay, so this disturbance causes deformation of a stationary longitudinal wave. Okay, stationary longitudinal wave. So the pattern is shown here. So again, yellow dot is the antinodes, which is the maximum displacement, also known as the amplitude. So when the frequency of the tuning fork coincides with the fundamental frequency, resonance will again takes place. So resonance is the occurrence of a maximum amplitude when the driving frequency is equal to the natural frequency of the system that is being forced into oscillations. Okay? Alright, so now let's look at for closed pipe lah. Okay, sekarang kita tengok untuk closed pipe pula. So closed pipe, if they ask you to find wave speed untuk closed pipe, sepatutnya untuk stretch string saja. It's not for, oh never mind, it is for stretch string saja. Okay, so for the first harmonic, which is the fundamental mode, the lambda is equal to 4 times the length of the string. Okay, so if we are to calculate the fundamental frequency, we are going to use V over 4L, where V here is the speed of sound. Okay, speed of sound. It will usually be given in questions lah. Okay, and then untuk third harmonic, okay, see ya, first harmonic and then tiba-tiba dia third harmonic. Okay, untuk close end punya pipe, untuk first overtone, it is no longer second harmonic, it is now third harmonic. Okay, untuk third harmonic, the wavelength is 4/3 of the length of string. Okay, so we can see that now dia ada 3 pula di atas. Okay, so 3. Sekarang ada 3 di sini. Tadi ni ada 1 saja, tidaklah 1 dia tulis. Okay, now let's look at the fifth harmonic. Untuk fifth harmonic, it is the lambda is 4/5 of the length of string. Okay, so how do we determine it? Miss sudah lukis lah sini. So this is 1 lambda, and then this is just a quarter of the lambda. Okay, so add this together, you can get 5/4 lambda. So if we want it in terms of length, we could just rearrange it lah. Okay, so for fifth harmonic, dia punya frequency, we can see that tiba-tiba ada 5. Okay, so again we can see the pattern here. So this is 1, 3, and 5. So if we remove that, if we let that 1, 3, and 5 equal to n, we can then get a formula, a general formula untuk closed pipe. Okay, so this is the general formula to find the frequency at a certain harmonic. Okay, so untuk closed pipe, only odd harmonics are allowed in vibrational modes, for example flute and recorder. Okay, so we also have a situation where we have to use n correction. So n correction is C. Okay, so n correction is actually known as, oh, it's not, I have to wait, let me check what does n correction means. I actually forgot what is that, and it's not in this note, so I'm trying to find. Okay, so end correction is an antinote that does not form exactly at the open end. Okay, for example, contohnya dia ada extended, so sepatutnya this thing here dia tidak end at this point, dia extend sikit lagi macam tu. So this distance is known as the end correction. Okay, so if dalam question we can neglect end correction, then you don't have to consider it. But if dia cakap ada end correction, so you are gonna use this formula here lah. So dia just add plus C di bahagian length tu, bahagian length di sini tu. Okay, so maksudnya dia punya string tu ada additional measurement lah, known as the end correction. Okay, tapi dia still end dia equal to 135, just tambah C di ujung. Alright, so that is on closed pipe. And then this is for open pipe. So this is where the air column with both ends are open. So again, the progressive longitudinal wave is disturbed by a source of sound, which is the tuning fork. Then this wave will be superposed with another progressive longitudinal wave by the air outside the pipe. Okay, so it causes a formation of longitudinal wave, and then the pattern of the stationary wave is shown here. Okay, aduh, dia terlari. So it is shown here. So it will produce an antinotes and notes in the middle of the pipe here. So this is the notes, and then this is the antinotes lah. Okay, so again, if resonance occur, a sound with a very high intensity can be heard lah. Okay, right, so now let's look at the first harmonic untuk open pipe. So for the first harmonic, the lambda is equal to 2 times of the length of string, and we can again calculate it by using this formula. So V here is the speed of sound. Okay, so V is the speed of the sound, and then if we look at the second harmonic, the lambda is equal to the length of the string. So this one, the F is 2V over L, 2V over L. And then for the third harmonic, the lambda is equal to 2 over 3 of the length of string. And then we then get this value here. Okay, so again, we can then see a pattern from this formula here. So we can generalize that into a standard equation, a general equation, which is this one. And then the value of n this time is real numbers. Okay, it's no longer odd numbers, it is just real numbers. Okay, real numbers start from 1 2 3 up until 4 5 6 7 gitu lah. And then at this point, all harmonics are allowed lah. Okay, so basically what it means is at fundamental they are the first harmonic, and then they go to second harmonic at the first overtone. Okay, the differences between this and the closed pipe is not all harmonics are allowed, as untuk closed pipe it only allows odd numbers lah. Okay, at the first overtone they only allow third harmonic, not the second harmonic. Okay, alright, again, this is an example for closed open pipe is clarinet, and that if you have to consider end correction, just add L plus 2C di hujung pula. Okay, di sini ada 2C. The harmonic number is the real numbers masih lah. Alright, so yeah,